Status.
Bodyguard.
Commander.
Rico.
Mission.
Mission. We're going to war.
Welcome to the Toys of War, a concise review of some of the modern trends in military research, military hardware, and the latest developments in military industry.
The Joint Strike Missile, JSM, is a product of Norwegian-American cooperation, born from Kongsberg Defence and Aerospace's need to adapt its successful Naval Strike Missile, NSM, for the air. Development began in earnest around 2008, with U.S. defense giant Raytheon joining the program in 2014 to help expand its global reach and integrate the system with the F-35A Lightning II. The missile's defining feature is compatibility with the F-35's internal weapons bay. Unlike many long-range cruise missiles, which are too bulky for the F-35's stealth-preserving internal bays, the JSM was specifically redesigned from the NSM to be slimmer and longer. This allows it to be carried internally without compromising the aircraft's radar signature. This adaptation also makes the JSM the only missile in its class to provide true long-range strike capabilities from inside the F-35A. The JSM has an estimated range of over 500 kilometers, depending on altitude and flight profile. It employs GPS/INS navigation, terrain-following capability, and a sophisticated infrared seeker with autonomous target recognition for terminal guidance. The missile is also network-enabled, allowing in-flight updates and retargeting, ideal for modern, dynamic battlefields. Its low RCS design and sea-skimming trajectory make it highly survivable. The Royal Norwegian Air Force plans to achieve full operational capability with the JSM aboard its fleet of F-35A by 2025. The missile has already sparked international interest, with Australia selecting it in 2022 to equip its own F-35. Japan has also signed a contract for JSM procurement, and other nations operating the F-35A are evaluating the missile for integration, recognizing its balance of stealth, precision, and range. The Hypersonic and Ballistic Tracking Space Sensor Program was initiated by the U.S. Missile Defense Agency to address a growing need. The capability to track advanced missile threats, especially maneuverable hypersonic glide vehicles. In 2019 to 2020, contracts were awarded to L3Harris and Northrop Grumman to develop competing satellite prototypes capable of persistent global missile tracking, from launch to terminal phase. To test the viability of both designs, the MDA launched 2 prototypes, one by each contractor, into low Earth orbit in 2024. These satellites were tasked with validating real-time tracking of dim, fast-moving targets, a key weakness in existing missile defense architecture. The trials aimed to determine which system could provide precision handoff data to fire control interceptors, a requirement for integrated missile defense. Both prototypes employed advanced infrared sensors and onboard processing, but L3Harris emphasized higher fidelity tracking algorithms and faster data relay via mesh networking. Unlike legacy systems focused on ballistic arcs, these satellites were designed to detect unpredictable flight paths typical of hypersonic threats. Real-time analytics and low-latency comms were core upgrades over the older space-based infrared system constellation. On April 25, 2025, the MDA confirmed that the L3 Harris prototype had successfully met all testing objectives. Northrop Grumman's satellite, while operational, fell short of performance benchmarks. With this decision, L3 Harris secured the lead role in the HBTSS program's future phases, including scale-up and integration into the broader Space Development Agency's missile tracking layer. Following this selection, L3 Harris is expected to begin deployment of operational HBTSS satellites starting in 2026 to 2027, in alignment with the SDA's broader Tranche 2 architecture. These next-gen satellites will be a critical component in a global sensor web designed to detect, track, and support the interception of emerging missile threats with unprecedented precision. Leidos, a major defense and technology integrator, plays a central role in advancing U.S. military systems, particularly in air defense. In 2021, Leidos, alongside Dynetics and Raytheon, was awarded a contract to develop the Indirect Fire Protection Capability Increment 2 launcher system. The project emerged from earlier concepts dating back to the mid-2010s, when the Army sought a mobile system to counter diverse aerial threats beyond the reach of existing short-range solutions. The IFPC-2 system is designed to defend critical infrastructure and forward operating bases against cruise missiles, rockets, artillery, mortars, and unmanned aerial systems. It fills the mid-tier gap between MSHORAD and Patriot systems in the Army's layered air defense architecture, enabling flexible, mobile response to modern threats. The launcher is mounted on a trailer and capable of firing Tamir interceptors, Skyhunter, with potential integration of Sidewinder or Stinger in the future. One of IFPC's greatest strengths is its full interoperability with the Integrated Air and Missile Defense Battle Command System. IBCS connects sensors and shooters across domains, allowing real-time targeting and engagement from the best-positioned asset, regardless of where the detection occurred. IFPC's modular, open architecture ensures it remains upgradable and adaptable to future missile types and emerging threats within the broader kill web. Testing has been ongoing at White Sands Missile Range in Fort Sill, where the system has successfully demonstrated live intercepts of both cruise missile surrogates and U.S. targets. The system's performance was validated, confirming its capacity to receive targeting data from external radars and execute engagements seamlessly. According to Army officials, limited operational deployment is anticipated as early as 2025, with broader fielding expected to follow in 2026 and beyond. The Storm Shroud is a compact, lightweight electronic warfare drone developed under a UK Ministry of Defence initiative based on the Tokaver AR-3 platform. Initiated in the early 2020s, the program sought to deliver a cost-effective, rapidly deployable asset for tactical EW and signals intelligence missions. It's part of the UK's move toward modular, adaptable unmanned systems that can enhance battlefield awareness and disrupt enemy operations. Designed with low observability and autonomous operation in mind, Storm Shroud is not a high-speed or long-range system. With a cruising speed around 65 to 80 knots, 120 to 150 kilometers per hour, operational ceilings up to 15,000 feet, and an endurance of about 8 to 10 hours, it's optimized for quiet persistence over an area of interest. Its effective mission radius is roughly 100 to 150 kilometers, depending on wind and payload. Rather than accompanying fast jets, Storm Shroud plays a complementary role. It can loiter ahead of or parallel to planned air operations, jamming communications, disrupting radar, and injecting false signals. It may also act as a decoy, forcing enemy air defenses to activate and expose themselves. It's part of a layered EW approach, softening targets for fast, stealthy aircraft like the RAF's Typhoons and F-35s. The onboard payload includes a flexible suite of electronic surveillance and jamming systems, possibly including direction-finding antennas, software-defined radios, and GPS spoofing tools. Modular design allows for mission-specific loadouts, including ISR, intelligence, surveillance, reconnaissance, sensors, or SIGINT tools tailored to theater needs. Storm Shroud is expected to reach full operational capability with the RAF by late 2025 or early 2026, following successful trials under the UK's Rapid Capabilities Office. It will likely serve in conjunction with other uncrewed systems under the UK's Mosquito and Protector programs, forming a flexible swarm-enabled electronic warfare toolkit suitable for both peer conflict and hybrid engagements.
If you find information in this video interesting, please like and subscribe.